Alright, 6.5. Today we get to graph square root and cube root functions. As with any other functions, we're going to start by looking at the parent functions of both. As you know, we can't put negative numbers into a square root, so we notice the domain is x is bigger than or equal to 0 for a square root function. Turns out that the range is also y is bigger than or equal to 0 because when you take the square root of a number, you always get 0 or bigger. So there's our parent function for square root of x. And the numbers I typically plug into that when I'm graphing it are 0, 1, and 4, because those are easy numbers to take square roots of. Notice I don't use 2 or 3 because I don't know what the square root of 2 or the square root of 3 is necessarily. Cube root of x is a little bit more robust. It's got more going on. We can take the cube root of any number, so the domain is all real numbers, and we can make x as big positive or as big negative as we want, so that makes our range all real numbers as well. Numbers I typically like to put in my table for a cube root on the parent function are -1, 0, and 1, because those are easy numbers to take cube roots of. And one thing to remember about cube roots is just kind of how the shape works. When you plot those points, it's going to look like a straight line goes through the 3 points, but we don't want our graph to be a straight line. We want to give it that curve that you can see in the parent graph. And that middle number in my table always is where the curve kind of changes from going uphill to going downhill. No, not uphill, downhill. Should choose better words than that. And right side up bowl to an upside down bowl. In calculus, we'll learn some words for that. It's called concave up and concave down. But for now, you just got to know it's that middle point is where it kind of switches gear. Still going positive slope, but it's not getting steep as fast. So let's take a look at a function. I'm going to invent my own word called a modified parent function, which means I want the same thing as a parent function, except I'm going to leave the number in front. If there's a shift, I strip away the shift from my modified parent function, but I keep that a in front. So I've got my modified parent function, which happens to be the same as the original here. We'll see a shift later in examples. Then I have to make a table of values. And as I said earlier, I like to plug in 0, 1, and 4. So when I plug these into my modified parent function, I can see square root of 0 is 0 times 1/2 is 0. Square root of 1 is 1 times 1/2 is 1/2. Square root of 4 is 2 times 1/2 is 2. So I can draw that graph. 0, 0, 1, 1/2, 4, 2. My graph looks ugly. I'm going to use real graph paper and plot those points. And we plot the points and get the graph. It's asking us for the domain and range. We can see from the picture that the domain is all real numbers bigger than or equal to 0. So is the range. And it says compared to the graph of y equals square root of x. You could graph that on the same paper, or you could realize that 1/2 is going to be a vertical shrink, and you would write that out in words. We've got a vertical shrink compared to y equals square root of x. Same kind of idea in example 2. I'm going to use a modified parent function, which means use the same function as the original, but take away the shift. There is no shift, so my modified parent function is the same as the original function here. And I still like to plug in my easy numbers. And go ahead and do that on your own, see if you get the same numbers as me. And then plot those points. Then we'll check in before I actually draw the curve. Alright, I talked about this at the beginning when we were looking at the graphs of the parent functions. It looks like we've got a straight line. Don't draw a straight line. Instead, ask yourself, where's my middle? Start there and draw a curve that kind of starts looking sort of flat as it goes out in both directions. And that's what our cube root graphs look like. If we want to compare that to the graph of y equals cube root of x, just a quick reminder what the parent function kind of looks like. Looks like we flipped it upside down and did a vertical stretch. So you could say reflected across the x-axis. That's another way of saying upside down. And we know that happens because of the negative. The reason we know this is a vertical stretch is because of the 3. So we should have been able to say that stuff without even drawing the graph. Again, the negative in front reflects across the x-axis. The 3 makes a vertical stretch. All right, go ahead and pause this and see what it's doing. It does say use a graphing calculator. You don't actually have to, it just makes it a little easier. Once you've got your graph, which you could do with a table or a graphing calculator, it's asking you how long is a pendulum with a period of 3 seconds. So we want to know when 3 equals 1.11 squared to L. You could check this on the graphing calculator. I think it's not really necessary. We could just solve for L pretty fast on our own, just by dividing by 1.11 and then squaring both sides. Turns out that the pendulum is 7.3 feet long. Verify that on your own. At this point, you can pause the video and try these on your own, or you can do that later. Shifting radical functions. Good news is it works exactly the same way as shifting every other type of function we have seen so far, and that we will see for most of this course. So I won't even really talk about it too much. The H and K tell you where to shift. So let's take a look at this. First, I'm going to use my modified parent function, which means take away the shift. So all I'm left with is the negative 2 squared of x. I'm leaving off the shift, which is positive 3, positive 2. That's my first step. My second step is to make a table for the modified parent function. It's a square root function, so I like to use 0, 1, and 4, as we've already seen in previous examples. Fill in that table. We get some numbers. Now's where the new piece comes in. We're going to get a new table that comes from our shift. In this case, the shift was positive 3, positive 2. So we're going to add 3 to all of our x values. Get a new table. So do that first. Using the h, I'm adding 3 to all of my x values. 3, 4, 7. Then I use my y shift, plus 2, so I'm going to add 2 to all my y values. And I get 3 points, and I can draw my square root graph. One thing to keep in mind, the starting point on the modified parent function was here, so this is still the starting point. Remember, square roots have a starting point, so you want to make sure you put it in the right spot. Go ahead and plot these points and try to state the domain and range on your own before you look at my answer. It's worth noting that this looks upside down compared to the original parent function. That's because of the negative in front. And then that whole thing was shifted over 3 up 2. And it was also vertically stretched by a factor of 2. All that's visible in the graph. That's about as hard as these get. Now let's take a look at a cube root one. It's going to be the same steps. I recommend you try this on your own start to finish before you look at my solution. Only thing that I really recommend you keep in mind are my tips. 1, write the modified parent function. 2, take note of where your center point is. There's no starting point, there's a center point. And then apply your shift. So you should end up with 2 tables of values with 3 x values in each table by the time you're done. Then you draw your graph. Try that on your own. Before I actually draw my graph, I just want to again point out that center point. That really tells you where you're going to change your curve from getting steep fast to getting steep slow. And we get something like so. All that's left is stating domain and range. on these cube root functions, it's really simple because domain and range is always all real numbers. Square roots are harder for domain and range. Cube roots, easier. At this point, you can try one of these on your own, or you can do that later. Other than that, we are done with this lesson.